Alright, so tonight we're going to continue looking at the conservation of mechanical energy, which is when our final total mechanical energy is equal to our initial total mechanical energy, and we don't have any friction or air resistance. And then we're going to look at the work energy theorem that has final kinetic energy, initial kinetic energy, and any work done by friction or air resistance. So in this particular example, we have a bobsled up at the top of the hill. It starts at a velocity of 0 meters per second. So all of the energy it has is potential energy, gravitational potential energy. So based on its position, it has 600,000 joules of potential energy. Now in this problem, we're ignoring friction and wind resistance. So there isn't anything taking any energy away from our bobsled. So as it slides down the hill, it loses potential energy and gains kinetic energy. It's just a trade-off between the two. So by the time it gets to the bottom of the hill, all of the potential energy it had at the top of the hill is now turned into kinetic energy. So in this problem, we have a motorcycle. It's driving off the edge of a cliff. The cliff has a height of 70 meters. And our motorcycle has a velocity of 38 meters per second. So our motorcyclist has both potential energy because of that height and kinetic energy because of this velocity. Now, when the motorcyclist lands on the lower cliff, the motorcyclist has less potential energy because they have a smaller height. And if they have less potential energy, then they must have more kinetic energy. So, using our equation for energy, the potential energy is mgh, the kinetic energy is 1/2 mv squared, and down here, the potential energy is again mgh, and the kinetic energy is 1/2 mv squared, and in this particular problem, these two equations are just equal to each other, and the difference in velocity comes from the difference we have in the height. So if you haven't already written it down, you definitely need to have this in your notes. The conservation of mechanical energy, whenever we talk about conservation of mechanical energy, the equation we're talking about is just this equation. So, where the final kinetic energy plus the final potential energy, the total mechanical energy final, is equal to the total mechanical energy initial. So, your energy isn't changing, it's just being transformed between potential and kinetic. Alright, so we started to talk about roller coasters in class today. So here's Kingda Ka. Kingda Ka, we're going to see later this year when we go to Six Flags. And it has a vertical drop of 127 meters. And at the top of Kingda Ka, when you get all the way up here to the top, which is really awesome by the way, it has a speed of approximately 6 meters per second at the top of the drop. So up at the top you have both kinetic energy and potential energy. Now I'd like you to use this information to try and calculate the speed when it gets to the bottom, ignoring air resistance and friction and all that stuff. So why don't you pause the video and go ahead and try that. Alright, so hopefully you're able to solve that using this equation where mgh is your potential energy up at the top of the hill, 1/2 mv squared is your kinetic energy at the top of the hill, and 1/2 mv squared on the other side of the equal sign is your kinetic energy down here at the bottom of the hill. But you probably realized at some point that you didn't get the mass of the roller coaster. Well, it just so happens that since mass is in all of our terms, mass just cancels out, and we end up with a velocity of 50 0.25 meters per second. Alright, so that deals with conservation of mechanical energy, but what we're going to look at now in a little bit more detail is the work energy theorem. Which says that the change in total mechanical energy is equal to the work done by non-conservative forces, forces like friction and air resistance. Alright, so let's take a look at the Kingda-Cobb problem again, but this time we're going to consider forces like friction, because in real life there is friction, there is air resistance, so energy is not actually being conserved. So we're going to take a look at what happens. Alright, so here's the equation for work and energy when there is a non-conservative force doing work, like friction. Now just keep in mind that the work done by friction and the work done by air resistance is typically going to be negative, because friction points in the opposite direction than the direction you're traveling. So even though it says potential energy plus kinetic energy plus the work done by non-conservative forces, this work, if it's done by friction, is going to be negative. So it's taking energy out of your system. So looking at this problem in a little bit more detail, H1 is 127 meters. V1 is 6 meters per second. H2 is 0, because you're down at the bottom of the hill. V2 is 45 meters per second. And the only thing we don't know is how much work is done by friction. So I'd like you to solve this problem tonight and come in tomorrow with that answer.